In the second part of wet cleaning, we'll be discussing mainly on localized treatment, but before that we'll also revise what we discussed in last lecture. So there would be a review of the last lecture, and since I got messages from you regarding uh, many of you not understanding the chemistry part, so like adjusted water, pH and conductivity, so we'll be covering these things in a separate lecture arranged for you by the end of the course. And as far as the localized treatment is concerned, we'll be talking about the gelling agents, Agarose, Gellan gum, and Xanthan gum. This is the summary of all the wet cleaning processes, main wet cleaning processes, and in this, the localized gel treatment is the one that we'll be discussing today. The rest three we have already discussed. We are just comparing here the different processes. So what we can see in the diagram is that in immersion wash, the paper is completely dipped in water. So this process is very aggressive, less in control, but it is extremely effective. You can see the acidic components coming out of the paper into the water. Float wash is not as aggressive as the immersion wash because only the lower part of the paper is in contact with water. The front recto, which might be having some sensitive materials, water sensitive material, is not in direct contact with water. It is less in control, though it is more in control as compared to the immersion wash, but not exactly totally in control, but it is also effective. Blotter wash is not aggressive, somewhat in control, and it is also effective. The localized gel treatment is not at all aggressive because it is just working in the areas where we want to remove the stain, and it is quite in control and it is also effective. Now this is a video of immersion washing technique that I have picked up from my very old video on the complete process of paper conservation till mending. So I've just taken the portion in which I'm doing the immersion washing. Let's see what is in the video. Let me start it here. So in this video, I'm first of all dry cleaning the print with a soft brush so that there is no loose dirt over it before I put a protective coating to fix the ink. Because in the testing, we found that the ink might be slightly sensitive to water, so that is why we are putting a protective coating to fix the ink. And apart from that, I've also secured because this paper was very brittle. At the slightest touch, it would break off. Thin and brittle. So I've secured the corners which were coming off. They had a little crack, and this is done with the help of mylar sheet and Japanese tissue paper and mylar sheet. A temporary mending was done at that corner, and then it was secured with a mylar sheet. Now this print was then kept on a non-woven polyester sheet. This is it. And this sheet was again kept over the polyester film. Then we prepared it for the treatment, because if we directly put it in the water, it might get destroyed because it was very acidic. On the back we can see it is so brown because the back was in direct contact with the board of the frame. So we try to give a mist of ethanol water mixture so that the paper relaxes a bit. You can see it getting relaxed with a mist of ethanol water mixture. So once it is totally relaxed, we'll put another sheet of non-woven polyester on top of it. And for some time, I'll put a mylar also, so that it is completely evenly humidified. And then I'll take away the mylar and take the print along with the non-woven polyester above and below it to the tray with water for aqueous treatment. So here I'll slowly dip it into the water. I have used a glass sheet to take it down so that it is not an abrupt kind of dipping in water, and slowly I'm trying to wet it by tapping it from the front. And if this non-woven polyester sheet wasn't there, it would have been difficult. This paper was so thin and brittle that it would have broken, and in water, when the paper is wet, it becomes even more delicate. So these polyester, non-woven polyester sheets on top and bottom help in working with the print inside the water. And here you'll see in some time yellowish components will start coming out of the paper into the water. You can actually see the acidic components coming out. So this is quite effective, very effective when you dip an acidified or degraded paper in water. And we have already discussed that whether this water should be deionized or should it be adjusted, or should it be added with some other components to enhance the cleaning process, or some particular stain. So this water is now all yellow because of the acidic components that came out of the paper. Then we dried it under blotters and then kept the print under the weight by putting some felt over it, and then glass, and then weights. And we can see after some time that this print, the tide lines have lightened. A lot of acidic components have been removed. So this was the part where I was showing the immersion washing in the video. The next slide this is about the blotter wash. In the left picture, you can see that I'm wetting a blotter, and in the second picture, I have put the paper to be treated on the wet blotter, and in the third, this is a video. We can see that after some time, a lot of acidic components, the yellowish brownish components from water, have been absorbed by the blotter, wet blotter. So in this way also we can suck up some acidic components or stains from the paper if we think that the front of the paper is sensitive to immersion washing. Now coming to the localized treatment, that is the main focus of today's class. The localized treatment is mainly done with the help of gels or poultices. So a gel is a solid jelly-like soft material that can have properties ranging from soft and weak to hard and tough. Gels are defined as a substantially dilute cross-linked system which exhibits no flow when in steady state. By weight, gels are mostly liquid, yet they behave like solids due to a three-dimensional cross-linked network within the liquid. It is the cross-linking within the fluid that gives a gel its structure, that is hardness, and contributes to the stickiness or the tack. In this way, gels are a dispersion of molecules of a liquid within a solid medium. The word gel was coined by 19th century Scottish chemist Thomas Graham by clipping from the word gelatin. So gelatin has this property of gelling. So this characteristic that is of gelatin was called gel by Thomas Graham. And since gelatin is prepared from animal products, so there are many options now of gums which are of vegetable origin that have the same characteristic of gelling like gelatin. So they are replacing gelatin in many of the recipes. First of all, we'll talk about agarose. Agarose is one of the two principal components of agar and is purified from agar by removing agar's other component, agaropectin, which is not required. So agarose is a polysaccharide that can be used to form a gel, often used to separate molecules based on size. It is very frequently, it is mainly used in biotechnology when they want to separate different molecules from a mixture of molecules, say that have been derived from some cells. So they want to separate like a DNA molecule from some other molecule or different proteins. So basically agarose behaves like gelatin. Scientists can heat and cool a mixture of agarose to form a gel. Here in the left video, I am preparing 2% agarose. Initially, you'll see when I'm adding agarose, it is liquid. It is not at all like gel. So in this, we'll see that agarose needs heat to get that property of gelling once it cools after heating. So in the second video, I have put it in the microwave. I'll do it 2-3 times. It will come to boil. And then in the third video, you'll see that I'm putting it in a petri dish to form the gel. So after some time, right now again when it is hot, it is runny liquid, but after some time it will thicken and it will form a gel. Next is the Gellan gum. Gellan gum is a water-soluble anionic polysaccharide produced by bacterium Sphingomonas elutea. Gellan gum is a food additive typically used to bind, stabilize, or texturize processed foods. It's similar to other gelling agents, including guar gum, agar-agar, and xanthan gum. It grows naturally on water lilies but can be artificially produced by fermenting sugar with a specific strain of bacteria. Sample of Gellan gum is prepared by disposing chalcogel Gellan gum powder in ultra-pure water at room temperature, and this dispersion is heated to 80 degrees Celsius under stirring and kept for 10 minutes in these conditions of stirring and 80 degree. Let's see. So this is in a continuous stirring. We have to first put this Gellan gum according to the concentration we want. It can be from 2% to 5%, and we'll make it stir with a magnetic stirrer. So it's stirring now. In a moment it will move this powder of Gellan gum collected on the top of paper. So I'll have to correct it in a while, and you can see it in the next picture, rather video. Here it is continuously stirring, and there are two knobs in this instrument. The right one is to adjust the speed of the stirring, and left one is to adjust the temperature. So in the picture you can see that on the left knob is at 80 degrees Celsius. So it is to be kept in these conditions of stirring and 80 degree for 10 minutes. So then we'll pour this Gellan gum solution in a petri dish and in a tray also, because the right side, what you see, the Gellan gum thick sheet, more rigid form of gel, it was actually prepared in a tray, rectangular tray, and I think it is in the picture. Yeah, I'm pouring it in this white ceramic tray. Right now it is runny, but as it will cool, it will form a hard, rigid gel, which you can see on the right side. Now in this slide on the left, this is a picture where I have kept the Gellan gum sheet on a mylar sheet, and then I had put the paper to be treated on top of the Gellan gum. After some minutes, when I checked, the acidic components from the paper were being transferred to the Gellan gum. And after keeping it for some more time, we saw more and more acidic components, and even some of the unwanted reddish color on that paper had also come out on the Gellan gum. So this is very controlled. I have here, for just demonstration, I have put the whole sheet. You can do this process in a localized area of a painting or something. You can just take that much piece of Gellan gum and put it on the paper at the bottom or on top, depending upon the requirement. This is a diagram explaining how it is working. On the right side is the microgel, and on left side is a hydrogel. It is just water, but in microgel we are modifying it to improve its properties so that it can go in the texture of the paper, and it can make water go through the fibers and by osmosis pick up the water soluble impurities, and again is picked up by the gel. Next is xanthan gum. Xanthan gum is a polysaccharide with many industrial uses, including a common food additive. It is an effective thickening agent and stabilizer to prevent ingredients from separating. It gives a good texture to the food, like it is used in coffees, in making ice creams. Like when we make ice cream at home, at times there is some ice crystal formation. It is not as soft and smooth like the ice cream we get from market. So if you put a little xanthan gum, those ice crystals won't be formed in between and it would be more smooth. So it can be produced from simple sugars using fermentation process and derives its name from a species of bacteria used, Xanthomonas campestris. A water solution of xanthan gum, 2% weight by volume, and triethanolamine. If we make xanthan gum not just in water, but we add triethanolamine also, 5% volume by volume, it forms a viscous pH 8.5% gel that is stable over a wide pH and temperature range. Additional materials can be added to make custom cleaning poultices, oxidizing agents such as bleach, and most cationic materials such as ammonia cannot be used as they cause the gel to collapse. Xanthan gum gels can also hold non-polar solvents in intermolecular pockets, oil and water emulsion, a property which has the potential to greatly reduce the conservator's exposure to solvents. These gels rinse well, making them suitable for use on paper and textile. This table summarizes the type and action of these three gums that we have just discussed. If we talk about the type, xanthan gum is a viscous poultice-like thing. Gellan gum is a rigid gel. Agarose is also a rigid gel. As far as heat requirement is concerned for making of these gums or gels, xanthan gum requires no heat. Gellan gum requires 80 degree of temperature for 10 minutes in continuous stirring. Agarose also requires initial heating. The pH range in which these act is like xanthan gum can act from 2 to 12 pH. Gellan gum can act from 3 to 10 and agarose from 2 to 14. And if we look into that, what kind of other cleansing agents can be added to these gels for enhanced action, then we'll see that the chelating agents that are generally used in cleaning can be added to xanthan gum, but not to Gellan gum. Agarose can also take the chelating agents. And solvents, all of these three can take solvents with them. Enzymes are not taken by xanthan gum or Gellan gum, but some of the enzymes can be picked up by agarose gel to the cleaning point. And oxidizing agents like the bleaches, they cannot be carried by any of these gums or gels because they'll just collapse the gel or gum. So that is all for today. Thank you.